So thanks a lot, Ariane, for the introduction. Good afternoon to everyone. I will present, as you mentioned, the work that I've been doing at the Polytechnic. This work has been done together with my advisors, Francesco Sotil and Matteo Gatti. So I will be talking about excitons, and in particular, how can we measure them or study them through this technique called resonant inelastic X-ray scattering. And I will show some results that we have observed and we have done on aluminum oxide. So can you see my mouse? If I point, so yes, no?
Yeah, we can see on your pointer. So
let me first start by introducing what is a resonant inelastic X-ray scattering. So in this technique, in this scattering technique, we have that an incoming X-ray photon will be scattered through a sample. And by controlling the energy and the momentum of this incoming photon, and by measuring the energy and the momentum of the emitted photon, we can get information of the electronic structure of our sample. So it is important to highlight that with this technique, it will be dependent on the polarization. So by changing the angle of the sample, we can change the polarization of the incoming, and it also depends on the polarization of the outgoing photon. And since we are working in the X-ray regime, it could be soft or hard X-rays, this technique provides bulk information because these rays can penetrate quite deep in the sample. And because it is an elastic scattering, there is some transfer of energy from the incoming photon to the sample. And of course, there is the conservation of the energy and the momentum in the whole process. The most important thing and property of RIXS, and what I think it makes it more interesting, is the possibility to be element and orbital specific. Because since it is resonant, this means that we will tune the energy of the incoming photon to a specific state that we want to study. So normally, because of this reason, we perform these experiments in synchrotron facilities where we can have access to above the spectrum of wavelengths and energies, and also we can provide quite high intensities that we need in order to observe the photons that are scattered. So I wanted to explain also which kind of information we can obtain from RIXS and how do RIXS spectra looks like. So normally in RIXS, we plot the intensity or the accumulated photons that we measure as a function of the energy loss. So if you can resolve low energy excitations, you could, for example, measure phonons or magnons. And the traditional, most of the cases, the RIXS is performed to study electronic excitations, such as, for example, DD transitions and other kind of electronic excitations. And this is where I will focus on in this presentation. And in particular, I would like to put some emphasis on what is the role of the excitonic effects during this process. So in order to understand why excitonic effects might be important in the RIXS process, let me now explain in more detail what is happening inside the sample when we perform the experiment. So as I mentioned before, we will tune the energy of the incoming photon to a specific state that we want to study in our sample. So I call it mu. And we will therefore excite it to a conduction state, and we will create this intermediate state with a core hole that is very unstable, so it has very short lifetime. As a result, there will be a relaxation of the valence electron to fill this core hole, and we end up in a final state, which is also excited state. So this is direct RIXS, so we are considering just a direct example here. And what is important to notice that we will have an electron-hole pair in the intermediate and in the final state. So even though in the intermediate state is a virtual state, very short lifetime, the presence of the electron-hole pair and the interaction of these two particles could be very important and to determine the final state and also to reproduce properly experiments. So in the experimental side and also in the theory side, what has been done so far? Here I show you some RIXS results that have been done with two different codes, ocean and exciting, and they both compare the results with experiments in the case of lithium fluoride. So in this case, the experiment is in dotted line, and in this case is in black. In this case, the calculations has been done without including the core-hole effect. This means the electron-hole interaction in the intermediate state only, and including this core-hole effect. So of course here you see there is a quite good agreement with experiments when you include this intermediate electron-hole interaction in the intermediate state. On the other hand, similar results are observed when you calculate the Bethe-Salpeter equation to capture excitonic effects in the intermediate and in the final state, or if you perform independent particle calculations where you don't consider electron-hole interaction at all in the whole RIXS process. So again, there is an agreement in the case of the Bethe-Salpeter, especially at the peak, at the energy of the peak. So now, what we would like to do is to, instead of use all electron codes such as ocean or exciting, is to perform or implement the same RIXS studies in pseudopotential codes. And why do we want to do that? So there are two important reasons why we would like to explore the calculation of RIXS from pseudopotentials. The first one is that when we use all electron calculations, we have to define an atom where we will excite the core electron. So this means that we will be localizing the core hole in a specific atomic site, and this will prevent us from describing important effects such as interference that might occur if you excite several equivalent atoms or degenerate equivalent atoms or degenerate states in the same in the same process. And the second reason that is even more important is that not all the core states can be studied with all-electron approach. And this is because the all-electron calculations use a muffin team, and they consider the excitation contained inside the muffin team, the core hole inside the muffin team. So if you want to study, for example, a shallow core core excitation, where the energies are not that deep and the states are not very localized, then the state is not going to be fully contained inside the muffin tin, and therefore you cannot perform a RIXS study on these states. This is, for example, the case of the Al-2O3 edge in aluminum, which corresponds to excitations from the 2p states to the conduction band. And the last interesting point for us is that we could therefore treat a valent core state with the same footing. So by just setting up a pseudopotential that doesn't contain those shallow core states inside, so therefore we will be calculating them with plane waves. we can treat these shallow core states and also the valence states with plane waves. And during this presentation, I would like to specifically address the following questions regarding to the studies that we have done in this time at the Corporate Technique. So the first one is that if we do a measurement, a RIXS measurement, or if you calculate RIXS, which kind of information can we get from it concerning electronic excitations? And how can we analyze the RIXS spectrum? And the second question is if we can perform also accurate calculations of RIXS using a pseudopotential code. So in order to answer to these questions, I will first discuss the RIXS intensity of RIXS cross-section at the aluminum L1 edge in aluminum oxide. And I use this material because it is a wide bandgap insulator where we expect the excitonic effects to be important, and therefore we can study and analyze the role of them. And on the second place, we will compare X-ray absorption calculations and RIXS calculations at the aluminum L1 edge, calculated with all electrons and also with a pseudopotential code to verify whether the results are accurate. We will take as a benchmark the all-electron code, of course, and we will benchmark against using all-electron, and we will benchmark the pseudopotential calculations. So before going to the results, let me first detail what is the methodology that we have been using. We want to describe excitons, so the state-of-the-art technique to do this is the Bethe-Salpeter equation that we can express as these eigenvalue problems, where we can diagonalize this Hamiltonian and obtain the eigenvectors and the eigenvalues. And these are the excitonic eigenvalues because they will correspond to the excitation energies, including excitonic effects. In the Hamiltonian, we can express it as a sum of these terms, where we have the diagonal corresponding to the independent particle energies. This means the energies of the conduction states and the valence states without including any interaction. Yes. And also we have the Coulomb interaction that will give the local field effects. That is, these effects are given by the fact that when we apply an external field, then the system will react and will induce a field that in the case of inhomogeneous systems and also quite polarizable systems, it could be important and it will give contributions. And finally, we have the screen Coulomb interaction that accounts for the interaction between the electron and the hole. By the way, during the talk, I will refer as independent particle, IPA, independent particle calculations, LPA, calculations that include the independent particle term plus the Coulomb term, and the Bethe-Salpeter, the calculations that are performed by using the full Hamiltonian. On the other hand, if you want to describe RIXS, basically we have to describe the Kramers-Heinzelberger formula, that is this complicated equation that you can see here. In order to understand what it represents, here I put again the scheme that I showed before. So here you have the initial, the intermediate, and the final states. And so we have the transition operators in this case, depending on the polarization, on the dipole transitions, and in the denominator, and here K2 and K1 represents the K of the incoming and the outgoing photons. The denominator of the equation here represents the conservation of the energy in the intermediate state. This means the absorption process. And here in the right, you can see the overall conservation of the energy, where the energy loss, defined as the difference between the incoming and outgoing photon, must be equal to the energy of the initial minus the final state. Sorry, the final minus the initial state. So of course we cannot solve this because here we have the many body final, intermediate, and initial states. So we should represent this equation in another way, where we can replace it by some ingredients that we can obtain, for example, from the solution of the Bethe-Salpeter equation. And this is what I show here. Of course, it is a quite long mathematical development to get to the final equation, but I would like to highlight this intermediate step where we here arrive to an equation where we have expressed the intensity of the RIXS as a function of the polarizability of that we could calculate from the excitation of a core state to the conduction band, and polarizability that we obtain from the calculation from a valence to a conduction band. And then we also have again the polarization vector and the dipole matrix elements, because we have used the dipole approximation. And also here I also apply the Tandakov approximation. So if we replace the polarizability, in this case, I use these general indexes to refer that we can calculate it for a core conduction or a valence conduction transitions. We can express it as a function of the eigenvectors and the energies, excitation energies, that we obtain when we diagonalize the Hamiltonian that I explained before. And finally, if we replace this equation and we resolve clean a bit more the total expression, we can arrive to this cross-section or intensity for RIXS, where we have here on one side, well, the oscillator strength will depend, as before, on the incoming energy of the photon. And we have two terms here, two factors here, the probability of the X-ray absorption. This is quite similar to what we calculate when we do X-ray absorption. And on the other hand, you have these other objects that are given, that will describe the, let's say, the excitation pathways, because it somehow connect dipole matrix elements that goes from valence to core with eigenvectors of calculations that are from core to conduction and from valence to conduction. And we have here the conservation of the energy in the complete process. And this is the spectrum that we obtain as a result. In the case, this is the K edge, I mean, this is the L1 edge, but the spectrum is very much the same as the L1 edge. But the energies are corresponding to the L1 edge. So what have I plotted here is the energy loss that I referred before as the energy of the incoming minus the outgoing photon. And here we have the X-ray absorption spectra, because it is always helpful when we calculate it or when we do experiment to have this reference to see that at each energy that we are exciting, where in the X-ray absorption we are. And especially because the behavior is quite different if we are exciting in this region or if we are exciting in this region. So we can identify two different kind of features in this spectrum. On one side, we have here what we call Raman features, because appear at a constant energy loss. And these Raman features are, I would say, the most important one in RIXS, because they depend strongly on the incoming photon. So this highlights somehow the coherence or the coupling that we have in this technique between the absorption and emission. So as a result, you see that the curve changes the shape with the incoming energy when you change the incoming energy, but also the peaks remains at the same energy loss. On the other hand, we also observed fluorescence features that appear usually when you excite at energies much higher than the X-ray absorption threshold. And in this case, the peaks move together to move, let's say, appear at increasing energy loss, which means that it is actually constant emission, because you will increase the absorption and then you keep constant emission, so therefore you increase the energy loss. And these features are normally associated to just X-ray emission or fluorescence, because this means that you have lost the coherence or the coupling between absorption and emission, and just the absorption will give you a modulation of the intensity, but won't change the shape of the spectrum. So sometimes, because of the nature of these two different features, we analyze them separately. And here I will describe briefly how we can compare them to other spectrum that we obtain, for example, with non-resonant RIXS. So here again I show the question that we arrived before for the RIXS. And we compare the RIXS losses with the losses that, for example, we can compute with non-resonant RIXS, or non-resonant X, let's say, non-resonant elastic X-ray scattering. So in this case, we are getting information in non-resonant RIXS. We are getting information on the structure factor, which is proportional to the imaginary part of epsilon, the electric function, the macroscopic electron function, the inverse, let's say. So by comparing the two equations, we would expect that the peaks that we measure or calculate with these two methods appear at the same energy. However, if you see here the oscillator strength or the intensity given by this part here of the equation, and in this case in non-resonant X, are very different, and they follow different selection rules, because in one case we have the coupling between two processes, absorption and emission, and in this case you will have just a scattering process that as a result give you a valence excitation, which is equivalent to the final state in RIXS. But the way that you arrive to this final state is completely different, and therefore the selection rules are different, and this is reflected here. We see that some peaks appear in the structure factor, and we don't see them in the RIXS spectrum. And this is we associate this to the fact that when we excite from the L1 edge, this means that we are exciting from two s states of aluminum to the bottom of the conduction band, which has mostly S character. So in this case, this transition is forbidden. So the minimum energy peak that we will see around these energies, we don't see it in RIXS because this first step absorption in RIXS is forbidden. On the other hand, when you have, for example, the excitations from the top of the valence band to the bottom of the conduction band, top of the valence band is mostly P character, and the bottom of the conduction band is S character, so you will have this transition allowed. And on the other hand, we can compare also the fluorescence features to the X-ray emission. As I mentioned before, since this is mostly fluorescence, meaning that we have the peaks at a constant emission energy, as you can see here. And the important thing here, I also plotted the independent particle results in green. And in the case of the low energy, when we are exciting at the threshold, we see that below the threshold or the threshold, we see that the independent particle calculations actually give quite different results. They don't reproduce very well the RIXS that we obtain with the Bethe-Salpeter. So this means that included excitonic effects is mainly important when we want to describe the RIXS features. Sorry, the Raman features. Okay, so this was concerned the first question that we wanted to answer. And now the second question is if we could use the pseudopotential code to calculate the RIXS. And before studying directly RIXS, we have to also compare the results in the case of X-ray absorption, because we know that the absorption can be understood as an intermediate state of RIXS. So, and it's also the most delicate point, because the X-ray absorption, and these I give here two examples, L2-3 and the L1. We have to go high in energy, and we are really have to test that pseudopotentials we have well converged with the plane waves, and even so, if the pseudopotentials give a good description of these excitations. So in the L2-3 case, we will have excitations from the 2p states to the conduction band in aluminum, and the L1 from the 2s states to the conduction band. And I show results for all-electron in red, and in all-electron in blue, and independent, and in red the pseudopotential results. The most similar spectrum are found, let's say, for the L2-3H in the three cases, independent particle, RPA, and Bethe-Salpeter. And in the case of the L1H, we have small differences, especially in the absorption intensity, because, as I mentioned at the beginning, when we do all-electron calculations, we just perform an excitations from one of the atoms. So then if we want to contrast with the pseudopotential, where you have 4 degenerated states, that you have to consider them all, you have to multiply by 4, but this is not exactly, it doesn't recover exactly the same intensity. This means that there might be some interference effect that are present in the pseudopotential case that gives a reduction in the intensity. So one last step will be to calculate the RIXS spectrum with pseudopotential, and these are preliminary results that we have obtained recently. Again, we have the energy loss for different and the absorption and the RIXS for different incoming photon energies. And I plotted here in blue the potential results, and in orange the all-electron results. So if you see the peaks follow at different energies, you see them that they follow the same energy loss. However, the intensities might vary quite a lot, and this might be, we have to do further studies, but this might be related to the fact that we are again having 4 states in the potential case, and this implies that we have more transitions that can, when you sum all the transitions, you can have that gives different interference, let's say. So at the end, we have the peaks that doesn't follow the same intensities. Notice that here we are, in all the cases, we are normalizing by the maximum in each case. So the densities may also vary if you take the absolute values. So finally, some conclusions. So we have observed that for energies that are close to the X-ray absorption onset, the RIXS spectra showed a Raman behavior. And this means that the losses remained constant when the incident photon energy was varied. And on the other hand, we also observed that at higher energies beyond the X-ray absorption threshold, the RIXS can be seen as a 2-step fluorescence behavior, where we have lost the coherence between the absorption and the emission process. And therefore, we see that the features move with the incoming photon energy. And finally, we also have shown that we have clear differences when we include and when we ignore the electron-hole interactions in both intermediate and in the final state. And that if we want to, regarding the pseudopotential implementation, we have already obtained a good description of the X-ray absorption with pseudopotentials, which is already a big step. But now, well, regarding the RIXS, we have observing some small differences, and this might be related again to the fact that there are interference when we consider all the atoms in the system. So finally, some outlook. So we have performed measurements of RIXS on boron nitride at the Fermi free electron energy laser and the line magnetine, and we have to analyze the results and see if we can see some dynamics of the exciton in boron nitride. And something I forgot to mention is that we have already performed measurements on aluminum at the L edges, but they weren't very successful since we observed mostly photoluminescence. So this is something that sometimes we can calculate the spectrum, but then it's much easier because then in the experiment you have a lot of other variables that you have to consider. And in this case, we observe photoluminescence. So we should repeat these measurements to using some filter to see if we can reduce this, and we can see actually the RIXS at the L2-3 and the L1 edge. And well, finally, currently, if you are familiarized with the Bethe-Salpeter equations, you realize that these are quite heavy calculations. So optimizing and having a good parallelization of the code to do this as fast as possible is critical, especially if you have to solve 2 Bethe-Salpeter equations in order to get one RIXS spectrum. So now I will be working on improving this implementation by improving the polarization, let's say, and seeing if it's possible to implement one scheme that's been already done in exciting, which consists in interpolating the density and actually the Hamiltonian. So I wanted to thank you for your attention, and I wanted to thank the codes for, well, I use open source codes. I wanted to thank also the funding that I received for my postdoc fellowship in the first 2 years, and also the institutions.
Thank you very much, Laura, for this nice talk. So there's time for questions now. So if you have a question, please raise your hand in the reaction section. Okay, we see them live because we see your Zoom. So Lorenzo, go ahead.
Yes, thank you. Congratulations for the work. So I have a question that may trigger a second question. Is about the pseudopotentials that you use. Maybe you said it and I lost it, but how technically you include the core hole? Are really different pseudopotential with an explicit core hole, or you do something else?
No, so sometimes when there are pseudopotential calculations on RIXS before, well, I don't know if they are still using this technique, but they used to prepare a special pseudopotential, as you mentioned, with a hole, and then they use this special pseudopotential for one of the atoms, and then they perform on top of that the Bethe-Salpeter. But in our case, our pseudopotentials are simply pseudopotentials that don't contain the states that we want to study. So this means that if we want to study the aluminum L1 and L2O3, this means the 2s state and the 2p states of aluminum are not inside the pseudopotential. So we treat them explicitly with plane waves. And we do a Bethe-Salpeter calculation as you would do a Bethe-Salpeter for valence, electrons, but in this case with these deep energy electrons.
I think I understood. So it's not explicit in the pseudopotential itself. But anyway, you should be able, maybe, if I'm not wrong, you should be able to enable this calculation only from specific atoms. I think of it. Because you said that the discrepancies, like here, the discrepancies you see with all-electron codes and yours are maybe due to the fact that in all-electron codes, the hole is localized on a specific atom. So I was wondering if you can check this assertion by enabling your pseudopotential calculation only for one atom out of 4 and leave like a standard method for the other 3.
So the thing that when we describe with the excitations with the plane wave, so we get, if we are studying the 2s states, 4 bands corresponding to the 4 aluminum atoms, and they are degenerated, and the result of the spectrum is wrong if you include just one of these bands or 2 of these bands. So actually in this, I don't know if the system, if other states much deeper, that could be possible. But in this case, that the energies are not very deep, you have to include the 4 bands apported by the 4 aluminum atoms.
Okay. Well, thank you.
It's also a limitation of the potentials. Let's say if you want to look just at one atom, then you have to make sure.
Okay.
Can I comment on that?
Yes.
Sure, Francisco. Yeah.
Okay. Maybe I got another view of what Lorenzo asked. Because if I understood correctly, Lorenzo suggests something like, I have 2 aluminum atoms in my cell, and I treat them differently.
exactly.
I treat one aluminum atom with the method that we do, so with the pseudopotential that contains the 2s and 2p in valence. So,
okay.
And another aluminum atom in which it will be without any, so it will be two different species.
Yes,
And
basically.
in that case, the core states will be only coming from one atom. Is that your question, Lorenzo?
Yes, yes, exactly.
That's a good point that could be tried. However, as you see there, in the difference is really small, really small.
Mm.
And I don't know if it actually this difference in treating them, two species in a different way, so different cutoff, it will be or on the same order or bigger. But yes, in principle, this could be a possibility to have only one atom in where we create the excitations.
Okay. Just since you mentioned it, it means, by the way, that the pseudopotentials you use for these calculations require a higher cutoff because there are much faster varying plane waves, or not?
Much higher. So
Much higher. Yeah, okay.
It's on the order of 2,000 electron volts.
Yeah, it was what I expected. Okay, no, it's horrible.
It's a
Okay,
lot.
thank
And this
you.
also yes, a bottleneck in the sense that it takes makes the calculation quite heavy.
Yeah. Well, okay. Thank you very much. Very good work.
Thanks a lot for your question.
Okay, thanks, Lorenzo. There's a question from Michael.
Yes, can you hear me?
Yes.
Sorry, wait a moment. A problem with the audio. Can you hear me now?
Yeah, we can hear you. Yeah.
Okay. So first, thank you for the nice talk. My question is related to the L2-3 edge. How are you treating the spin orbit splitting? Are you treating explicitly using fully relativistic pseudopotentials, or so this is the question for the L2-3 edge.
Yes, unfortunately, we don't have an implementation to treat explicitly the L2-3 splitting, and this is not very. I mean, it's 0.5 electron volts in this case. So this, as a result, gives that the exciton, this peak, is actually double peak. Separately by this small energy, but the rest of the energies, the rest of the peaks are quite well described with our pseudopotentials. But yes, that's something that we haven't done so far, especially because it is not implemented.
No, I just an idea could be to just compute L2 and use the experimental splitting and get the L3 using the region, but yeah, it would be more complicated to use explicitly the fully relativistic pseudopotential. Okay, thanks.
Thank you.
Thank you. I was wondering, so you're doing the experiments yourself on these materials to compare, or I mean, you're waiting for the experimenters to obtain the measurements, but are there maybe other materials for which there is a RIXS spectra available to which you could compare, or are those calculations too expensive?
I'm sorry.
No, I just wonder if there's some material to which you compare for which you can do the calculations and for which there is experimental data available.
Yes, so on one side, no, it's not. So I participate from the experiments, but in fact, the experiments have been conducted in the case of the aluminum oxide in Soleil. So we did it together in collaboration with Alessandro Nicolau, who is one of the main researchers of the line sextants, and they did most, of course, of the experiment because I am not familiarized on how to do it. So we participated from the discussions. And on the other hand, well, and also we are a team. We were a team that also did experiments in boron nitride in Fermi. And also again together with experimentalists that they have more clear experiment on one side on RIXS and also in time resolved RIXS. Again with Alessandro Nicolau and Marco Malestudfo. I didn't mention his names. So, and the second question regarding other, the possibility of performing other calculations and in fact comparing. So we started with aluminum oxide because it was something that we didn't know that we wouldn't be able to measure at the moment. So we just found out last week, and now we will see if it's possible to measure. We'll try again, or we could test with other materials. But when we chose the material to do all the studies, we were quite optimistic that it will be possible to measure.
Okay, but in the literature, there must be some
yes.
experimental data on other materials. But so I guess, I mean, your calculations, of course, are very expensive. So I don't know how easy it is to.
In fact, here I show lithium fluoride, but you can find cuprates, a lot of RIXS experiments done on cuprates and other much more complex materials. It's not very frequent that they do experiments on simple materials. So also it's if you want to choose a material to do the calculations, you have or limitations that we have with DFT and so on. So and also the number of atoms that you can include, and you cannot afford to reproduce any experiment that is survivable.
So these are RIXS spectra?
These are experimental spectra.
And the calculations also. But so did you try to compare to the, I guess, the excited? So these are all electron calculations. Did you do also did you get similar results for the pseudopotential results?
With pseudopotential, no, but actually, if you see here, these are being done for the KH. So these energies are much out of the range of energies that we can access with the pseudopotential formalism.
Okay. Yeah.
We can describe excitations with pseudopotentials at up to 150. Well, yeah, 150 to I don't know. I could say 200. But we cannot access definitely these energies, and I don't think that we can go much beyond that.
Yeah, of course. Okay. Yeah. Okay. Thank you. There's a question from Nicolas.
Thank you.
Can you hear me?
Yes.
So just a curiosity, can you do D to D transition, or say, do you include the finite momenta of the photon here or not?
No. So let's look at this. So in the equations or the momentum, we do dipole approximation. So we don't consider the momentum of the we don't consider neither the momentum of the incoming nor the outgoing photon. So
Okay.
Everything is treated on the dipole.
Okay. Perfect. Thanks.
Thank you.
Okay. Thanks, Nicolas. Any other questions? Last chance. Okay, I don't see any further questions, so it's almost 3 o'clock, so maybe it's a good time to stop. So thank you again, Laura, for the nice talk, and everybody for the discussion, and hopefully see you next time.